Hi all. In the previous video we discussed about what kind of questions can be asked in induction machine in the gate examination. So in this lecture what we will do is we will continue from where we left off and we'll see some more type of problems that are usually asked in gate. So the next topic that we will be dealing with is losses and efficiency of an induction machine. Now is in like in any other machine, for finding the efficiency or losses, we need to understand the power flow diagram. So in case of induction motor, how does a power flow diagram look like? So first we will have electrical input, then we will have stator core loss, then we will have stator copper loss. Then what we get is the air gap power. Then we will have rotor copper loss. Usually there are rotor core loss also, but we assume that the total core losses occur in the stator. Then we get developed power, or it is called as mechanical power. Then we have friction plus windage losses, and we get the shaft power output. Is it fine? These rotor copper losses are equal to S times Pg. That is why developed power is 1 minus S into Pg. That is our developed power, or it is also called as mechanical power. So usually rotational losses, if it is given, it is sum of two loss, that is core plus friction plus windage. These two losses combinedly are called as rotational losses in an induction machine. Now let us see the problem that is given to us. It is saying a 3-phase 400 volt 50 Hz induction motor takes a power input of 35 kilowatt. So PE we know as 35 kilowatt. Now as you see here, we know the frequency but we do not know the number of poles. So we cannot predict the synchronous speed. So in such a case, what we have to do is, in order to know the synchronous speed, we have to take the closest possible speed to the full load speed. Now full load speed is given to us as 890 rpm. So the next possible synchronous speed closest to this is 1000 rpm. Okay, which exactly fits in the formula of 120 F by P if we have 6 poles. Is it fine? So stator losses are given as 1 kilowatt, which means I can find out air gap power. It is electrical power minus stator loss. 35 minus 1, that is 34 kilowatt. Friction and windage losses are at the last step, so I did not need to consider this. What is the slip first of all? So for slip, Ns minus Nr by Ns will be the slip, that is 0.11. What about rotor copper loss? The rotor copper loss is SPG 0.11 into 34, that is 3.74 kilowatt. Now what about shaft power? So we know shaft power is obtained by subtracting friction and windage losses from developed power. And what is developed power? Air gap power minus rotor copper loss, that is developed power, minus friction and windage loss. So it comes out to be 28.76 kilowatt. Now it is asking us shaft torque. How to obtain shaft torque? Shaft power upon rotor speed. Shaft power is 28.76 kilowatt. Rotor speed is 890 rpm. Convert it to radian per second. So it comes out to be 308.58 Newton meter. Okay. Remember, the numerator is in kilowatt, so you have to consider a factor of 1000. And the last one, efficiency. We know the shaft power output 28.76. We were given the input power, that is 35 kilowatt into 100. So what we get here is 82.17%. So that is the efficiency of the induction machine. Let us see another problem based on the same concept here. So it is saying a 400 volt 3 phase 6 pole 50 hertz. So first step should be to calculate NS. 120 into 50 by 6, that is 1000 RPM. Draws a power of 2 kilowatt at no load. At no load, the power corresponds to rotational losses, which means core loss plus friction and windage loss. That is given to us as 2 kilowatt. Okay. Usually what happens is we neglect I square R losses at no load. That is why I am saying the power taken at no load is equal to core loss and the friction loss. At full load slip of 3%, that is SFL is 0.03. The power input is 50 kilowatt. Okay. And stator ohmic loss is 1.5 kilowatt. Okay. So stator copper loss is 1.5 kilowatt. If stator core loss and mechanical loss, what is meant by mechanical loss? Friction and windage loss. Both are equal. Now we know sum of these two losses is 2 kilowatt and both are equal, which means core loss and friction and windage loss each is equal to 1 kilowatt. So the first thing that we need to find is the rotor ohmic loss. So we know the copper loss inside the rotor is equal to slip times the air gap power. So first we need to find air gap power, which is input power minus stator copper loss minus core loss, 47.5 kilowatt. Now we know what is rotor copper loss. It is slip times the air gap power, which comes out to be how much? 1.425 kilowatt. So the first part is solved here. Next we need to find the shaft power. Now we know shaft power is developed power minus friction and windage loss. So again I'll tell from shaft power. Shaft power is developed power minus friction and windage loss. So developed power, how we can calculate? Air gap power minus rotor copper loss minus friction and windage. How much is friction and windage? 1 kilowatt. So this shaft power will come out to be 45.075 kilowatt. Next is shaft torque. Again we can calculate shaft torque in a similar manner. That is, T shaft 45.075 into 10 to the power 3 divided by speed. Now how much is the speed? We know synchronous speed is 1000 RPM, slip is 0.03. Convert it to radian per second by multiplying with a factor of 2 pi by 60. So it is 443.746 Newton meter. Next is internal torque. Internal torque is developed torque. So it is nothing but developed power upon omega r. So instead of 45.075, you have to use the developed power, which was 46.075. So this will come out to be 453.591 Newton meter. Now what about efficiency? Efficiency is shaft power by input, which is 45.075 by 50 into 100. So this is 90.15%. So that is how we can calculate the losses and efficiency inside an induction machine. You just have to remember the relation between the mechanical power, rotor copper loss, and the air gap power. Along with that, also memorize the power flow diagram. The next type of question can be asked based on determination of equivalent circuit parameters of an induction motor by conducting no load and the blocked rotor test. Now this no load and the blocked rotor test, they are pretty similar to what we do in transformer as the no load and the short circuit test. So in these type of problems, you must be very well aware of the formulas that you need to use. So let us see this. It is saying a 15 kilowatt 440 volt 6 pole delta connected. Remember, in case of three-phase machine, this connection matters very much. Gave the following test result. No load test is given, blocked rotor test. Now DC resistance of the winding is 0.8 ohm. We need to find rotational loss and equivalent circuit parameter, and we have to assume a factor of 1.2 for the skin effect. Now stator resistance would be 0.8 into 1.2, 0.96 ohm. This is due to the skin effect. AC resistance is higher than the DC resistance. Now first let us focus our attention on the no load test. In no load test, the impedance is voltage by current. Now current should be taken as 10 by root 3y. It is line current, and in delta connection, phase current is line current by root 3. And in delta connection, line voltage is phase voltage. That is why I am taking current as 10 by root 3. So this will come out to be 76.21 ohm. Okay. Now we need to calculate no load resistance. The power is 280 watt divided by 3 times I square. Because any real power is 3 times I square R. Why? Because it is a three-phase machine. So this comes out to be 2.8 ohm. Based on this, we can calculate X no load as Z no load square minus R no load square. So this should come out to be how much? This will come out to be 76.158 ohm. Okay. Now we have X no load as 76.158 ohm and R no load as 2.8 ohm. Okay. So the first thing that you need to determine is the rotational losses. So how will you determine rotational loss? We know under no load, whatever the losses have occurred, it will be rotational loss, which means core loss plus friction and windage loss, and also the stator I square R losses. So rotational is total minus I square R losses in the rotor, 3 times I square stator resistance is 0.96. So it is 184 watt. Okay. Remember, rotational losses mean core losses and the friction and windage loss. So under no load, usually in stator, copper losses also occur, but we neglect them usually. But when you are testing the machine, you will have to consider them to find an accurate value of the rotational losses. Now let us focus our attention to the blocked rotor test. Is it fine? So we have determined rotational losses by the use of no load test. Now we will go to blocked rotor. So what is the impedance in blocked rotor test? 100 voltage by current. Current will again be 40 by root 3 due to delta connection. So how much will this come out to be? 4.33 ohm. Now what about blocked rotor resistance? Losses divided by 3 into current square, that is 1 ohm. What about reactance? Under root Z square minus R square, this will come out to be 4.213 ohm. Now the first formula that you need to remember is for the leakage reactance of stator and rotor. Both are equal and they are equal to half of XBR, that is equal to 2.106 ohm. So that is the first parameter of equivalent circuit that we have derived. Next is magnetizing reactance. It is XBR minus X1, X no load minus X1. X no load we derived as 76.158 and X1 is 2.106. So it comes out to be 74.05 ohm. Now the only thing that remains between us is the rotor resistance. Because we know stator resistance, we need to find rotor resistance. So the formula for rotor resistance is, it is R blocked rotor minus stator resistance Xm plus X2 by Xm whole square. So RBR was 1. This was 0.96. Xm plus X2, it is actually equal to X no load 76.158 over 74.05 square. So this comes out to be 0.04 ohm. So that is how you can derive the equivalent circuit parameters of an induction machine. You have to first remember this formula, then magnetizing reactance, and then the rotor resistance. Is it fine? And how do we calculate the stator resistance? We calculate it by the use of voltmeter ammeter method, in which we can measure the resistance of the winding directly. So next we come to how to start an induction motor. In starting of induction motor, you have to remember three methods: direct online starting, then star delta starter, then auto transformer starter. In direct online starting, whatever is the starting current is also called as short circuit current. In star delta, the starting current is reduced to 1 by 3 and the starting torque is also reduced to 1 by 3. Similarly, in auto transformer, the starting current is reduced to x square as well as the torque is reduced by a factor of x square. X is the transformation ratio of auto transformer. X is less than 1. So here in starting, the case is we want to reduce the starting current from a high value to a manageable value. But at the same time, we are also losing upon the torque, that is your starting torque. But these many formulas are enough if you wish to remember for the starting of an induction motor. Now let us see what happens here. It is saying the starting current of delta connected 3-phase induction motor at rated voltage is 5 times the full load current. At rated voltage, starting current is also called as short circuit current. It is 5 times the full load current. And full load slip is 0.05. Now we need to know if an auto transformer is used to limit the starting current from mains to 2 times the full load current. That means it is saying I starting by I full load is 2. Now if you take ratio of these two equations, I starting by I short circuit is 2 by 5, which is equal to x square. Okay. We need to estimate the starting torque as a percentage of full load torque. Now starting torque upon full load torque in case of auto transformer is x square ISC by IFL square SFL. Now x square is 2 by 5, ISC by IFL square 5 square into 0.05. So it comes out to be 0.5. That is 50% of the full load torque will be produced as the starting torque. Next it is asking, if we neglect the stator impedance, what is the slip for maximum torque? Now see, we saw one formula in torque slip characteristic, that was T by T max is equal to 2 by S upon SMT plus SMT by S. Now this formula if you use for T starting, You have to keep slip as 1. So it will become 2 times SMT over SMT square plus 1. If you use it for full load, you have to keep S is equal to SFL. So this becomes SMT square plus SFL square. Now if you take the ratio of starting to the full load torque, it is also equal to I short circuit by IFL square SFL. So why I am using ISC and not the starting current? That is because in order to take the ratio of the torques, you have to keep the voltage same. That is, we have to use the rated voltage. If I am using rated voltage, it means direct online starting, in which starting current is equal to the short circuit current. Is it fine? So that is why I am using ISC and not X square ISC, which means the first part has nothing to do with the second part of the problem. Now if you take the ratio, what will ratio become? T starting by TFL. 2 times, 2 will get cancelled out, or let me first explain it. 2 SMT by SMT square plus 1 into SMT square plus SFL square by 2 SMT SFL. This is equal to 5 square into 0.05. Now this gets cancelled out. 2 gets cancelled out. Here we know that full load slip is equal to how much? 5%. So by using this equation, you can calculate the value of SMT. SMT will come out to be 0.253. So remember, when we are dealing with such a problem, or if you are dealing with T starting by T max or T by T max, in that formula the voltage must remain same. That is the essential condition. Otherwise that formula will not be applicable. Next, let us see another problem based on starting. A 50 kVA 440 volt 3-phase 50 Hz induction motor is provided with a 3-phase step-down auto transformer which steps down the voltage to 50% of input. It implies X is 0.5. Moving ahead. Given that starting current of motor on rated voltage, is ISC is 6 times the full load current. So ISC by IFL is 6. Estimate the current drawn by auto transformer from the mains at starting. We know I starting by IFL is X square into ISC by IFL. That is 0.5 square into 6. That is 1.5. So starting current is full load current. How we can calculate? 50 kVA by root 3 into rated voltage into 1.5. So how much is the starting current? That is 98.412 ampere. That is what is your starting current. What is starting kVA? That is root 3 VL into IL. That will be 75 kVA. This we could have calculated directly, since we know starting current is 1.5 times the full load current and voltage is same, which means the kVA will become equal to 1.5 times of the rated value, that is 75 kVA. 1.5 into 50. Okay. Next question. A 3-phase delta connected squirrel cage induction motor has starting current of I delta and starting torque of T delta. Starting current and starting torque while the motor is started through star delta starter and auto transformer with 60% voltage are T I star and T star and I auto and T auto. We need to find the ratio. So what is the ratio of I star by I delta? I told you earlier as 1 by 3. I auto by I delta, that is x square. X is given as 60% or 0.6. What about t starting by t delta? That is again 1 by 3. What about t auto by t delta? That is again x square, that is 0.36. These formulas are very important if any problem is asked based on starting of induction motor. So more importantly, you have to remember two type of starters, star delta and the auto transformer. Next question is based on speed control of induction motor. Now mostly the problems that are asked on speed control of induction motor are more or less based on the torque slip characteristics. So if you have understood those things well, then you can solve these sort of problems also. But you have to remember one or two concepts additionally. Now here is first of all for the V by F control. So V by F control means V by F shall be taken constant as we increase the frequency. Now in this type of problem, if it is given to you that the torque is also constant, you have to remember this condition, that ns minus nr will remain constant. This is very important condition if we derive a constant load torque using V by F control of induction motor. The other thing that you need to remember is the curve of voltage versus frequency is somewhere like this. So the curve is linear from a low frequency up to rated frequency. After that you can increase the frequency, but voltage should remain constant because voltage cannot be increased beyond the rated value. Now let us see the problem given to us. An AC induction motor is used for a speed control application. It is driven from an inverter with a constant V by F control. The nameplate details are given to us. So first let us find out NS. Initially the NS should be 3000 RPM, which is the closest possible synchronous speed to the rotor speed. What about rotor speed? 2850 RPM. You can calculate slip here. 3000 minus 2850 by 3000, that is 1 by 20. Now the motor is run with the inverter output frequency set at 40 Hz. In such a case, what will be synchronous speed? We know synchronous speed is proportional to frequency, so it will be 2400 RPM and half the rated slip. So slip will become half, 1 by 40. Now what will be the rotor speed? 2400 into 1 minus 1 by 40, that is 2340 RPM. Is it fine? So in V by F control, this was a direct problem which you could have solved. But in problems where torque is given as constant, the difference between synchronous and the rotor speed must remain same. The next method that is used for speed control of induction motor is EMF injection. So what happens is, in case of slip ring induction motor or wound rotor induction motor, we inject a voltage externally into the rotor. That will change the rotor voltage. So V dash is equal to V plus minus injected EMF, plus if they are in same phase, minus if they are in opposite phase. By that logic, since the torque is proportional to V square, the torque also changes. But if torque is constant, slip will have to change. Okay, because torque is also a function of slip. If slip changes, the rotor speed will change. Is it fine? So let us see the problem that is given to us. A 10 kilowatt 50 Hz 4 pole. So first let us find out synchronous speed 120 into 50 by 4, 1500 RPM. Has leakage impedance. So impedance is given to me, that is R2 plus JX2. When delivering full load torque, the motor runs at 1440 RPM. So that is the first speed that is given to me. Based on this, I can calculate the slip also. It will be 60 by 1500 or 1 by 25. Now we need to find the magnitude of EMF injected at rotor terminals for a speed of 1800 RPM. So for 1800 RPM, the slip will be minus 1 by 5. Now we need to find EMF injected for a constant torque load. That is, the torque should remain same at both the slips. So let us say after injecting the EMF, earlier the voltage was 60 volt. Now let us say it becomes X. So in both cases, the torque must remain same. So earlier the torque would be 60 square into R2 by S. R2 is 0.2 by S is 1 by 25. So this will become 5 square plus X square. That is basically R2 by S. That is what I have written in numerator. Now the voltage becomes X and R2 by S. We only take magnitude of the slip. So 0.2 divided by 1 by 5 is 1. 1 square plus 1.5 square. From here, if you calculate X, it comes out to be how much? It shall come out to be around 47 volt. Exactly, it is 46.33. Now earlier the voltage was 60. Now it is 46.33. So EMF injected is minus 13.67 volt. Minus implies that the induced EMF or injected EMF both are opposite in phase. Is it fine? So that is another method of speed control of induction motor. Other than that, one technique is known as pole changing technique, in which we reduce the number of poles, increase the number of poles by 2. So if poles become 2 times, the synchronous speed becomes half. Okay. And how do we change the number of poles? By reversing the direction of current. So these three methods are pretty important for speed control. Other than that, what methods we have already seen? In torque slip characteristics, we saw two methods. One was voltage control, in which I told you if we change the voltage, the slip will change, and based on change in slip, the speed will change. And the other one was rotor resistance. So based on these two methods, we have already seen problems in the torque slip characteristics. The last component of this chapter is a single phase induction motor. So usually in single phase induction motor, two type of questions can be asked. One is based on capacitor start induction motor and other is based on the torque slip characteristic. Now, as we already know that a single phase induction motor is not self-starting. So in order to make the starting torque high or make it self-starting, we have to use two phases. So one phase is known as main winding and the other one is known as auxiliary winding. But windings are usually inductive, due to which both will be lagging. Now to produce maximum torque, what we need to do is, we have to have a 90-degree phase shift between the windings. But in two inductive load, current cannot be 90-degree phase shifted. Why? One will be lagging, other will also be lagging. So the angle between them can be 30, 40 but not 90. So to make the angle between them 90, what we do is, we connect a capacitor in series with the auxiliary winding. So the first type of question that can be asked from you is, what should be the value of this capacitor to make the angle 90 degree? So see this problem. A single phase induction motor has stator winding in space quadrature, that is, both windings are kept at 90 degree and is supplied with a single phase voltage of 200 volt at 50 Hz. Main winding impedance is given, auxiliary impedance is given. We need to find the capacitor inserted in order to make the starting torque maximum. Maximum starting torque means 90-degree phase shift. So for this you have to remember the formula RA Rm by Xm plus Xa. Okay. So RA is auxiliary winding resistance, Rm is main winding resistance, Xa is auxiliary winding reactance, Xm is main winding reactance. So RA is 19.7 from the question, Rm 5.2, Xm 10.1 plus 14.2. So this comes out to be 24.342 ohm. Now once we have Xc, we can calculate capacitance. We know Xc is 1 by omega C, which means C is 1 by omega Xc. So 1 by omega will be 2 pi f, that is 100 pi. Xc is 24.34. So this comes out to be 130.76 microfarad. So this method is the shortest way of calculating the capacitance required for 90-degree phase shift. The next type of problem can be based on characteristics. So it is saying a single phase induction motor is provided with a capacitor and centrifugal switch. Now what is this centrifugal switch? This is a switch which opens by virtue of speed. So at a certain speed this switch gets opened. This switch is expected to operate at 0.7 ns, but due to malfunctioning the switch fails to operate. Now what happens in normal induction motor? The characteristics are like this. That is, there is zero starting torque. But if you have a capacitor, the starting torque increases and characteristics are like this. Okay. But we usually do, what we do is, we disconnect the capacitor in the middle. So we will trace this characteristic up to a certain value. Then we disconnect the capacitor and we return to the original characteristic. Okay. These are the characteristics of capacitor start induction motor, the one in blue. Okay. But it is saying due to malfunctioning switch fails to operate. That means we will fail to jump from the upper characteristic to the lower. That means we will go on following the orange curve. So answer will be C. Is it fine? So that is how we can judge the characteristics of a single phase induction motor. So these are the topics that can be asked in GATE examination from the induction machine. So this will be all from this lecture.